electric field is given the variable capital E as a vector. An electric field is defined as the projection of the opportunity of force in space. Now, what that means is that electric field is not a physical object that you can see. Electric field is instead something that we draw in order to make predictions of something that would happen if charges interacted. Now, traditionally, we draw Q to represent charge. And so let's suppose that this is a charged object Q. Now, it could be a proton, it could be an electron, it could be an ion, which is an atom containing a disproportionate number of electrons to protons, and therefore either having a positive charge or a negative charge. Regardless, what we know is that this Q will interact if we introduce another Q nearby. Now, this Q out here is given a lowercase q and is considered to be a test charge, right? The test charge is not actually there, right? We know that if we did a Coulomb's law problem where there were two charges, that the force between two charges would be the Coulomb's constant times Q1 times Q2 divided by the radius between them squared. However, if we just have one charge, what we'd like to be able to do is describe what could happen if there was a charge introduced at this point, but there isn't currently. An electric field is a way of doing that visually with lines. And so what we have to imagine is that any charge will emanate an electric field from it, because no matter what this charge is, this charge will either attract or repel to the larger Q here, right? And that's because all charges experience a force between them, no matter how far away they are, based on their interaction constant K. And so if we were to think about it, there could be a force vector line that would be drawn from this charge onto that charge, and it would either be going away from Q, in other words, pulling Q into the lowercase q, or it could be going towards Q, indicating that it was being repelled. In other words, the force would be this direction. So that means that all charges can have identifying force vectors in all different directions. Now, the number of lines that we draw to represent the electric field is arbitrary. However, it will be valuable to use logical numbers, rational numbers, when we're identifying the field, and I'll talk about that in a few minutes. Now, through convention, scientists have decided that the test charge is going to be a positive value. So what that means is that if Q is positive, then the force from this charge would be a repulsive force pushing Q away from the system. Now, of course, if Q was over here, then that would push Q, large Q, in this direction. And if lowercase q was here, that would push the charge in this direction. And if the lowercase q was here, that would push the charge in this direction. And so what we see is that when the Q is positive, the electric field lines are drawn indicating away from the charge. Now, they can be drawn like this, they can be drawn like this, etc. However, what we'd like to be able to show is that when we draw more charged electric field lines, the relative strength of the electric field is increased. And so in this case, we would count these as 1, 2, 3, 4. We would count these as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so the ratio of the magnitude of this charge as a positive value would be roughly 2.5 times larger than the magnitude of this positive charge. Now, of course, we could have started with 2 here and put 5 here, and we would have the same ratio. So again, the number of lines does not matter. However, based on the test charge convention, if the test charge is always positive, which it is, then if the center Q is a negative value, such as an electron or a negatively charged ion, then we know that the force from a test charge here would pull this charge towards the Q in this direction. And so the field lines for a negative charged object are going to be toward the negative, right? These are interactions towards the negative charge. And so what we see is that when the charge Q is positive, the electric field lines run away from the charge, and when the charge is negative, the electric field lines run towards the charge. Now, this is simply just a visualization tool, but what it allows us to do is combine charges. So if we put a positive Q here and a negative Q here, assuming that these are two charges in similar space, we would combine the line diagrams. Now, what we have to keep in mind is that a test charge that would be placed somewhere, say here, positive Q, would be repelled from this charge and attracted to this charge, which means that the force would be this direction no matter what, right? And this aligns with our given diagram, away from positive and towards negative, which means that given the absence of the actual charge, we could still identify an electric field line that goes in one singular direction from positive to negative. Now, of course, if the positive charge was over here, positive Q, it would be repelled from positive and attracted to negative. However, the negative is further away from the test charge than the positive is away from the test charge. And of course, the relationship of force is an exponential to the distance, so the positive would win and the overall force would still be away. Whereas if we were over here, the test charge Q would be attracted to negative more so than it would be repelled from positive. So this side, the electric field would be in towards the negative. This side, it would be away from the positive. Here, it would be away from the positive and towards the negative, which is one consistent going to this direction. Now, those sets of lines all make sense, but if we look at one of the vertical lines, we see that things change ever so slightly, because if there was a test charge here, positive Q, it would be repelled from the positive in this direction, but attracted to the negative in this direction. And if we combine these two vectors, what we see is we get a force that's going somewhere like this, which means that the field line at this position is actually pointed more to the right. And so if we were to extrapolate this, that means that the lines that are coming vertically away from positive are actually curving to go from positive to negative. Now, this would be symmetrical in this direction, positive to negative. And then, of course, we could extrapolate other ones where this would be from positive, looping out in some gigantic loop, coming back around and being directed towards negative on this side. Similarly and symmetrically, the same thing would happen, here and here. While there are no calculations, no numerical values that we can be referenced from this, electric field line diagrams are often a useful tool for simply visualizing what would happen once we solve the solution of Coulomb's law. So if I have positive charge here and a positive charge here, when I look at the line diagram, I know that the electron or the positive test charge would be repelled from either extreme horizontal directions, but the vertical lines, of course, would be repelled in a more extreme way. If I put a charge that was here, I know that it is repelled vertically upward due to this charge, but it is also repelled this direction due to this charge, which means that the net combination is something more like this. So if I were to look at a charge field line, it would probably look something like this, repelled away from the system. This allows us to demonstrate the fact that if I were to put a test charge here in the middle, I am already aware that here in the very center between these two objects, there would be a net force of 0 because the two would cancel out regardless of their horizontal displacement. And so we would have a cancellation of the forces, and the net force on this would be 0. It's useful to know this information because then we can predict the motion of a charge as it would move through the field without actually having to calculate the individual vectors and do the vector sum. And so an electric field line diagram is useful for visualization of the concept and confirmation of an overall result, but not the only tool for solving the solution.